Hi everyone. Today we'll be looking at calculation questions about the moment of a force. But before we get started, it's worth reminding ourselves about how the equation works. If you imagine a small object on one end of a seesaw with the seesaw's pivot point somewhere around the middle, then that object's moment or its turning effect in that direction is going to be equal to the weight of that object, its force acting downward, multiplied by the perpendicular distance, d, from the pivot point there to the object over there. Now remember, perpendicular means at right angles, and as you can see, that distance d is at right angles to the line of action of force acting that way. We can add in numbers to calculate the size of this moment. For instance, if that distance there is 2 meters and the size of the force, the object's weight, is equal to 4 newtons, then the moment of the force m in the clockwise direction is going to be equal to 4 multiplied by 2, giving us a moment of 8 Newton meters. The unit for perpendicular distance is the meter, the unit for force is the newton, and the unit for the moment of a force is the Newton meter, or Nm. That's one of the easiest units to remember because it's just a combination of newtons and meters. In order to balance the clockwise moment on the right hand side, we need an anti-clockwise moment on the left hand side. This can be generated by a large object over here. If the anti-clockwise moment on the left-hand side equals the clockwise moment on the right-hand side, then we can say that the seesaw is in equilibrium. Of course, if the size of the force changes, for instance to 8 newtons, then the perpendicular distance needs to compensate, since to get a moment of 8 Newton meters, we need a distance of 1 meter. Since 8 times 1 gives 8. Notice how, for the object on the left generating an anti-clockwise moment, the force downward is greater, but its distance to the pivot is less than that of the object on the right-hand side generating a clockwise moment. This matches what we'd expect to see in everyday life. For instance, if I'm trying to balance objects on a ruler, and if the mass on the left-hand side is double that on the right-hand side, then the distance on the left-hand side needs to be half that of the right. In this example, the clockwise moment acting this way is equal to the anti-clockwise moment acting in the opposite direction. However, if I were to move the mass on the left-hand side further along, the object is no longer in equilibrium because the anti-clockwise moment is now greater than the clockwise moment. This is because, even though the distances are equal, the force on the left is greater, which is why when I let go, the object isn't stable and the whole thing falls apart. Sometimes you might be asked to use the concept of equilibrium to solve a problem when you're not given one of these 4 values. So for instance, taking a look at this problem over here, we are looking at finding the missing value of f, knowing that this seesaw is in equilibrium, meaning that the clockwise moment on this side is equal to the anti-clockwise moment on the other. We'd start just by working out the moment on the side with which we've got 2 values, and that would be m equals f, which is 9 newtons, multiplied by d, which is 1. So that's obviously going to give you a value for m of 9 Newton meters. That has to be equal to the moment on the clockwise side. Moving on to the clockwise moment of m equals f multiplied by d, we know that the distance is 3 meters, but we don't know the value of f, that's still unknown, and we do know the value of m using the value of the anti-clockwise moment, since they're equal. Bringing a number over here, we've now got this equation, 9 equals f times 3, and through simple algebra we should be able to see that f equals 3 newtons. Let's move on to more challenging work. Here we have a question where the moment of a force is linked to other parts of the curriculum. This is a wire balance, which means that we have a conductor balanced along a metal support. There is a weight on one end, that's the insulating bar, and there is a force acting on the other end due to the magnetic field. Because the conductor, the wire, is balanced along a point, this point, the metal support, effectively acts as a pivot. And I'll label that on the 3D diagram on the top and the 2D diagram at the bottom. When approaching a long calculation question, the first thing you should do is underline or circle what you're trying to find. In this case, that's magnetic flux density, and the question has reminded us of that at the bottom where you're meant to write the final answer. Next, you should of course highlight the relevant information and numbers presented in the question. In this case, we've got 5 centimeters for the length of the wire. We've got 1.5 amps for the current flowing through the wire. We've got a clockwise moment of 4.8 times 10 to the minus 4 Newton meters. And I believe that is all the information over here. Looking through the rest of the question though, you may have missed the perpendicular distance between the pivot and the force due to the magnetic field. That's 8 centimeters over there. And let's label that with the symbol D. You'll notice how I've labelled the quantities I've been given with their relevant symbols. In an exam, you could of course use words to help you through. Let's also put in the symbol for the unknown quantity, the magnetic flux density that we're trying to find. Next, let's work on any relevant unit conversions. We know that the base unit of length is meters, and therefore 8 centimeters and 5 centimeters need to be changed to 0.08 meters and 0.05 meters respectively. Moving on, let's take a look at the physics equation sheet to try and find something relevant. At GCSE, there's really only one equation that has magnetic flux density, and that's force equals magnetic flux density times current times length. Writing that out, we've got F equals B times I times L, and we are now going to substitute numbers that have been given. We've got a length of 0.05 meters after conversion. That's a small letter L, by the way, sorry for the handwriting. And we've got a current of 1.5 amps. B is of course unknown, as that's our magnetic flux density, so I'm going to colour code that red because that's what we're trying to find. And interestingly, we also don't have a value of F. There is nothing in this question that's measured in newtons, so I'm going to label that in blue because we're going to need to find F to finish this problem. Now, you may have noticed we have not used the value of the clockwise moment yet, and you will hopefully remember that the moment of a force, M, equals F times D. That's also given to you in this equation sheet. So, writing that equation out, we've got M equals F times D. We're going to substitute values that have been given. We've been given a value of M of 4.8 times 10 to the minus 4. We've been given a value of perpendicular distance D of 0.08 meters after conversion. And that will allow us to find the value of F that we need for this earlier equation. So, rearranging that, you will get a value for F of 6 times 10 to the minus 3 newtons, which is a fairly small number because this is after all a wire balance. Now, putting that number back into this equation over here, we are going to get 6 times 10 to the minus 3 equals my unknown flux density multiplied by 1.5 times 0.05. And before we rearrange to get our final answer, it's worth noting that substitution does get you a mark in the final exam. So for instance over here, you would have got 1 mark for that line and another mark for this line over here, just for putting in the right numbers. This is why you should always try to substitute before rearranging if you're not confident with the maths. Actually doing the maths though, over here, we've got our flux density B being equal to 6 times 10 to the minus 3 divided by 1.5 times 0.05, giving you a final answer of 0.08. However, the question does say give the unit, and that's why you need to remember to write Teslas at the end of your answers, or T for short. Just reviewing the steps in that question, we started by circling the quantity we were trying to find, highlighting all of the relevant numbers and doing the unit conversions, then finding an equation that would give us our final desired quantity. We then substituted relevant values, found any further values that were needed, in this case that was force, and rearranged to get a final answer, remembering to put a unit at the end over there. Let's try applying those steps to a harder question. Here, we've got a 2D view of a ramp that's being supported by a stretch spring on one end and being pulled down by its own weight over here. There is a pivot point that's been labelled for us, and we've been given several values. First off, circling what the question's asking us to find, we're looking for elastic potential energy. We're then going to go through and highlight relevant numbers that have been given to us. We've been given the extension of the spring over here, that's 0.250 meters. We've been given the moment caused by the ramp, that is of course the turning effect caused by its weight going down this way, and that's 924 Newton meters, which I'll label with a capital M. We've also been given a perpendicular distance in the diagram once again, that's 0.15 meters. We're going to label that with the letter D. And of course, we're going to use the symbol EE for elastic potential energy. You will remember that after identifying relevant values, we had to look through the equation sheet to find a relevant equation. Here, that's quite simple. We're looking for something that gives us elastic potential energy, and that's right here. EE equals half times the spring constant K times extension squared. Let's go ahead and write that down and substitute the numbers that have been given to us. So, we have a value of extension of 0.250 meters. Don't forget to square that when you put it into the equation. We don't know what the value of elastic potential energy is, and that is what we're trying to find at the end, so I'm going to color code that red. However, we also don't have the value of the spring constant K. So let's mark that out in blue, because we're going to need to look for that before we can find the energy stored. Now, what numbers have we not used yet? We have not used the moment of a force, and we have not used the perpendicular distance D. We are trying to find K. If you were to look through the equation sheet though, you would not find something that linked the moment of a force to a spring constant. So there is an intermediary step here. Let's start just by looking at the other equation with the spring constant, F equals KE. How did I know that F equals KE was the right equation here? Well, I knew I needed K, and there are only 2 times K appears in the equation sheet. This equation, Hooke's law, and the equation for elastic potential energy. And since I already used the elastic potential energy equation, I knew this had to be what I needed to find the missing value of K over here. Substituting values that have been given to us, we've got a value of extension of 0.250, which we used earlier. We're trying to find K. I'll mark that in blue. But once again, we don't have the value of force. There is nothing here in the question that's measured in newtons. So force is unknown, and we need an equation to help us find force, just like how we needed an equation to help us find K. That equation should ideally link the moment of a force and its perpendicular distance, and you've hopefully spotted that there's only one equation that does that on the equation sheet. That's moment equals force times perpendicular distance, m equals fd. Writing that down. Let's substitute relevant numbers. Our perpendicular distance is 0.15. The anti-clockwise moment is 924 Newton meters. And our force F is of course unknown. That's the reason we're using this equation, to try and find the value of F so that we can find the value of K to put into the original equation. Now, rearranging that, rearranging that, if you do it, you should get a value of F that's equal to 6160 newtons, and that number then needs to be substituted into this equation over here. So, writing out that line, we've got 6160 is the value of F, equals an unknown K multiplied by 0.250. And when you do the algebra, that's going to give you a value of K of 24,640 newtons per meter. Note, that's a spring constant measured in newtons per meter, not a moment measured in Newton meters. Similar units, but for very different things. We can now take this value and finally put it back into our original equation to find the value of elastic potential energy. So let's do that, and we should get something that looks like this. A half multiplied by 24,640 multiplied by 0.25 squared, giving us a final answer of 770 joules. So let's review. We read through the question, we circled what it was asking us to find, we highlighted relevant numbers, but didn't need to do any unit conversions this time. We looked through the equation sheet so that we could find something that would give us the value of elastic potential energy. We then realized we needed the value of K, found another equation that would help us do that. We then realized we needed the value of F, found a third equation, the equation for the moment of a force, and through sequential substitution, we're finally able to get a final answer of 770 joules. A somewhat cynical view here is that to do this question and the one before, you didn't really need to understand the physics. You just needed to have a good understanding of how to use an equation sheet. This year, remember, you're given every equation that you need, so make good use of that, and best of luck for your exam on Friday.